Okay, lecture 9, part 3. Let me talk now. I just introduced conditional proof. Talk about the form of indirect proof, and then we'll look at examples of how they're applied. Indirect proof has other names: reductio ad absurdum, or reduction to absurdity, a very commonly used form of proof in ancient times as well as modern. In our formal proofs, it's just you assume a thesis, you assume a formula, right? So P, of course, this is a sentential variable, taking as substitution instances any formula whatsoever, right? You assume some formula, and you derive a contradiction, right? It's otherwise called, we call it indirect proof, called reduction to absurdity, reductio ad absurdum. Contradictions are absurd, so this is the absurd thing, right? Assume P if applying the normal rules of inference and replacement rules, right? So formula goes here, formulas go here, formulas are P here, and if you are able to derive any contradiction, right? Anything in the form Q and not Q, again, Q is a sentential variable, so any formula at all, any formula at all, can be A by conditional B, right? Any formula and its contradiction, so that would be A by conditional B and not brackets A by conditional B, right? Anything in the form Q and not Q, if you can derive that, that will be the last step of your subproof, and you are allowed to infer on the main line, right? The line where things are just as true as your premises, you're allowed to infer not P, the negation of the thesis you assumed, or the negation of the formula you assumed, right? So this is the formalization of what is a very common mode of argumentation, right? You're arguing with your friend says, I think P, and you say, P? That's absurd, because if P was true, look, this follows Q, but also the opposite follows, not Q also follows. P can't be true, because if P was true, both Q and not Q follow, right? And that's what you derive. Somehow you derive Q here, and then a bit later you derive not Q, negation of any formula and its negation. And to properly apply the rule, of course, we are sticklers for rigor, you have to rigorously adhere to the structure or form of the rule. So the last step of the subproof has to be in the form Q and not Q. It has to be a conjunction. So what is this? The last step of any indirect proof has to be the conjunction of a formula and its negation. A conjunction of a formula and that formula's negation. Strictly that. That has to be the last thing. So you cannot finish a subproof and just go back to the main line if you somehow have Q here and then not Q. Look, I've done it, I've derived a contradiction. Now you've got to put it together. You miss that step, you lose points. But, right, having derived a contradiction, conjoined the two sides of it, you're allowed to infer in the main line the opposite, the negation of what you assumed, right? You assume P, you infer not P. Notice that is the form of the rule, right? We'll get to some applications in a minute, but it is not correct to it is not correct to assume not P, right, and derive P. This is not the form. It says not the form of the rule, right? It's not the case that you assume not P, you infer P, right? That's wrong. That's not right. The form of the rule, right? If you need to derive something which isn't actually a negation, working backwards, you'd have to double negate it, right? And you could assume not P, derive a contradiction on the last line that allow you to infer not P, right? Because this is the form of what we have above, right? You assume, right, when you conclude the proof, you add a negation to what you assumed. When you conclude the proof, you add a negation to what you assumed. That's the proper form. This is the proper form. So if this is going to be in the proper form where you start with the assumption not P, the conclusion, you have to add a negation to what you assumed. So the proper conclusion is not P. From not P, you can, of course, infer P by double negation. All right, so let's look at some examples of how to apply these two rules. Yes. Okay, so these are examples from the book. The first one's introduced in each section. So the first one is page 177A. So it's this one, page 177. Next one, so that's going to be, we're going to see conditional proof in action. The next one's from 181, right after they introduce you to indirect proof. So that's O, D. D at the top of 181. All right, so we're going to see these rules in action, and what I'm going to stress is the important difference between conditional proof and indirect proof in terms of knowing where you're going. Conditional proof has an advantage that indirect proof doesn't have. So, and if you grasp this, it's going to help you apply these rules properly. So this is an example of a proof you could be tasked with completing, right? Let's get rid of these things here. This is my kids' room. They have a chalkboard wall, which turns out to be useful. So my kids' bedroom is now my new lecture hall. Woo-hoo! All right. Okay, so you've got one premise, right, and one conclusion. Okay, so what was the mistake that I warned you against? Thinking that because the right way to do conditional proof is to always remain conclusion driven, right? You're looking at your conclusion, you're analyzing the structure of your conclusion, and when you say to yourself, oh, look, the conclusion is a conditional, very good chance conditional proof will be the best thing to use to derive this. The one premise is also a conditional, but you're not looking at that in thinking about how you're going to be applying conditional proof. Okay, this is a crucial point. Correct application of conditional proof is all about getting right what it is you assume and knowing what it is you're aiming for, right? When you use conditional proof, you'll be setting up a subproof, you'll be making an assumption, and what appears on your page is always, the first things that appear on your page are always the assumption at the very top, and for conditional proof, and this is the advantage conditional proof has over indirect proof, the first things that appear on your page are the assumption that you make, the specific formula, that's the assumption you make, and you draw your line like this, right? This is your subproof, and also, absolutely crucial, the conclusion of your subproof, right? The specific formula which you need to derive, and that is such that when you have derived it, you know you have reached the end of your subproof, right? Such that now, okay, whatever I put here, we'll talk about what that is in a second. You have the rule which allows you to derive that formula, but what's going to appear right now as I set up this subproof, before I do any specific derivations, right, is a specific formula. That's what's true of conditional proof, but not true of indirect proof. A specific formula will go here, and the key to correct application of conditional proof is knowing how to figure out what that formula is. But so that's going to appear, and then you'll be set up such that when you have actually derived that formula, you know, oh good, I'm done. That's the end of my subproof, right? Now, in the next step, I say, this is true, right? Assuming A, I can derive C, and this is justified by conditional proof, and the numbers are, in this case, will be 2, right? But I've got one premise, so the second step is going to be an assumption, and 2 through whatever number this is, 6, 8, 9. That's the justification for this. But the crucial thing you need to know, that you need to be explicit about to have a mastery of conditional proof, is knowing when to stop the proof, knowing when you have come to the end of your subproof, right? Now, the key to knowing that is not making that big mistake that I mentioned in introducing the rule before, right? Do not look at this conditional that you are given to determine what goes here as your assumption and what goes here that'll be the conclusion of your proof. Remain conclusion driven, okay? This is the conclusion you need to derive, right? You're looking at this formula. It is in specifically A hook C, right? This is what you will infer using the rule of conditional proof. This will be the conclusion of your subproof. This will be the conclusion of your conditional proof subproof, right? And this formula, right? The structure of it, what its